Hey, today we're going to knock out a Codecrafters challenge. I'm going to try to one-shot the whole thing in one setting, one video. We'll edit it up. I've done some in the past where it's like a playlist of videos. This one's kind of short, so I figured we would just see if we could do it all in one go. So buckle up for a long video. Get your code editor ready. We're going to write some Go, and we're going to jump into the Build Your Own DNS Server Codecrafters challenge. I've got the challenge up on the screen here. I'm already signed into Codecrafters. I've got the introduction right here. We'll go through it all, or we're going to go through every single bit of it. So if this is your first Codecrafters challenge, sign up. If you haven't yet, I've got a link in the description that will, in full transparency, it gives me a bit of a kickback, which helps me make videos like this and keep the channel going. It costs you nothing. But if you do decide to subscribe at some point, I do get a kickback. But it's completely free to sign up. They do free challenges, and the challenges rotate. So like if the DNS one is not available at the time that you're watching this, it will be at some point in time, I would assume. But yeah, check it out. So yeah, let's talk through that. And then if you have signed up, join my team. You can see here there's recent attempts from other people on the team, so you can see where their progress is at. So we're going to go through this one and knock it out. Okay, so we have an introduction here. It tells you a little bit about Codecrafters more than anything else. The preferred language that you'd like to use, you can pick your language here. We're going to do ours in Go. And yeah, once you click that, you'll see that the pre-challenge assessment is in progress. Your language proficiency. I don't really know what the difference is here. They say that we can tailor your experience accordingly. I've clicked beginner on certain languages and I've clicked advanced on other. I don't really know what the difference is. It might just be this blurb right here, to be honest with you, but I'm going to click intermediate. We'll go to next question. Cadence. I'm going to say once a week, and I do not want accountability. Don't email me on this. We'll get it all done right here in one go, hopefully. Okay, so what you get is this repo that you're going to clone. So I'm going to go ahead and copy this, and I'm going to go to an editor. And what we're going to do, I'm going to go to my YouTube folder here, and then I'm just going to go ahead and git clone, and then cd into Codecrafters DNS server Go. So once we have that done, all we need to do is push an empty commit. And this is just making sure that your environment is set up properly and everything is good to go. So I'm going to copy this, paste it. I use GPG keys to sign my commits, so I had that pop up. You probably won't unless you have GPG keys as well, in which case you know what you're doing and type in your your key. Okay, cool. So this is generally the flow for Codecrafters. You make some changes, and then what you do is you push your commits. It runs in CI. Some of the tests, and I didn't expect this one to already fail, but that might be intended. Okay, it looks like it is. So it'll run in CI, and it'll execute tests, and then it will update your status here accordingly, depending on that. So what our flow will be is we'll make some changes, we'll push some stuff up, hopefully things pass. A lot of times they probably won't. So we'll see what is failing, and then we'll work on fixes for that, and then we'll fix it and push it back up, and that'll be the flow. Okay, so once we've completed a step, we can hit View Next Stage. So take me to the next stage. Since this is the first stage, we've included some commented code to help you get started. To pass the stage, simply uncomment the code and submit your changes. Nice and easy. There are step-by-step guidelines that you can do, so you can mark these as complete. They might be useful if you're new. I generally don't do that. I might try just for this video to kind of organize things a little better, but generally I just do the whole section in one go. So it prompts you to open an editor. I have an editor open. I've got some Svelte stuff up here. We don't want that. We instead want some Go. So show me YouTube, Codecrafter server Go, and here we are. Okay, hopefully this is pretty legible. I'm going to also get in here and I'm going to turn off completions for, 2 hours. We'll see. Hopefully it doesn't take that long, but I really don't want completions. I would rather just type this all out manually and do this myself. So what we can do is we can come back over to Codecrafters. If you want to mark this as complete, you can. It even tells you what code you need to uncomment and like what the diff looks like. So in our case, we just come in here, uncomment this block to pass the first stage. So I'm just going to grab everything here and uncomment it. And then I will delete this message. Okay, we could just submit this. And in fact, let's go ahead and do that. So get status, I can get add, I can get commit, first stage. And then give this a push. And it should pass. Test pass, congrats, mark step is complete. So you can click this link, or we can just come back to our Codecrafters here and mark the stage as complete. I'm going to go ahead and click view next stage, but we're going to come back to that in just a second. We just uncommented some code. Let's actually talk about what it does, right? So one of the things I want to pull up to is some information about the DNS spec. I think there might be a link in the Codecrafters challenge, which might be useful. But what we're ultimately going to build is essentially something that is parsing DNS messages, and ultimately will end up using a forwarding server that it can send requests to hopefully furnish the DNS records. I think by the end of this, we only support A records. So, you know, you could grow this and support CNAMEs and text records and any record type that you would like at some point. And this will give you the foundation to start that. Okay. This is interesting. Ensures GoFump doesn't remove the net import in stage 1. Feel free to remove this. Yeah, we can go ahead and remove that now. Okay. So what we're doing is we're calling net resolve UDP address. So if you're unfamiliar with UDP, UDP is kind of the counterpoint to TCP. So TCP is like a handshake from a networking layer where you would reach out to me via TCP, and I would acknowledge that you're reaching out to me, and I would say, yes, I can accept your messages. And then you'd come back and say, okay, I'm going to send you a message that it looks like this. And then I'd say, okay, I'm ready to accept a message that looks like this. And then you would say, okay, I acknowledge that you're ready to accept a message that looks like this. Now I'm sending you that message, and so on and so forth. It's a bit of an involved process. UDP is just you sending me a message, and who knows if I get it. Hopefully I'm listening for it. There's not really a confirmation. There's no handshake to make sure that, you know, things are going to go well. UDP is essentially pretty... I shouldn't say there's no confirmation, because you can respond via UDP. But I guess what I'm getting at is there's a lot of pomp and circumstance around TCP and establishing handshakes to make sure the connections are good to go and everyone's ready to accept messages, and that packets will arrive in the correct order, or at least packets will arrive and then be resolved in the correct order. UDP doesn't really mess with all that stuff. UDP is just give me the thing and I'll give you a response. If you want to learn more about UDP, you can. There's plenty of great resources for that. I'm going to try to call out resources as we go. So, you know, you can find Wikipedia for UDP right here. One of the core communication protocols of the Internet Protocol Suite used to send messages, transported as datagrams and packets to other hosts. I was hoping that there'd be like a really high level that compares it to TCP. Right here, comparison of UDP and TCP. If you're interested in that and you want to learn more, I think this is probably a great place to start. And I'm sure that there are books and other things you could get into on network engineering that would be equally as thrilling to read. For us, though, we know that we're creating essentially a UDP address we're resolving here. And this gives us an address. So you can see it's a pointer to a net UDP address. You know, we check the error type. If error is not equal to nil, I'm going to assume that you know Go if you're watching this video. And if you don't, the tour of Go should cover kind of this pattern right here with error and error handling. Check out the tour of Go if you're unfamiliar with it, but I'm not going to go through the error handling because we're not going to do anything particularly crazy with our error handling for this. Now that we have that UDP address, we're going to call net listen UDP. This is actually going to start listening for UDP packets on that address. So you can see it acts like a listen packet for UDP networks. The network must be a UDP network name. You can see the dial func for more details. Yeah, so in our case, we are giving the network as UDP, and then the address is the UDP address that we created. We defer closing that because we like to clean up after ourselves. And then we make a buffer we have 512 bytes. Why do we have 512 bytes? I believe that is the package size for the DNS query. Let me see if I can find more information on that. Okay, it looks like actually that's covered in the next section, so we'll circle back to that in just a moment. And then we're using a for to essentially loop over some processing for as long as we can. It's read from UDP. So we have that UDP connection. We're calling read from UDP, and then we're passing in that buffer right up here that we're creating, that byte buffer. And then this is being written into, so you can see here we have receive data. We're taking a string of that buffer and its size that we get back from the read from UDP. So this is the number of bytes that have been read. And then we're printing received so-and-so bytes from, received size bytes from that source. And then we have the data here. And one thing worth mentioning too is, like this is 512, but it doesn't necessarily have to be 512. That's the cap, which is why we're getting the size of bytes that we've read from UDP, and then we're sub-slicing this to just the length of the size. We do need to respond, so we create an empty response. In our case, this is just a byte slice, and we write that back to our UDP connection via the write to UDP method. So we have our response here, and we have our source, which is the net UDP address, and then again, some Go error handling. Okay, let's talk about DNS. So we're on the next section now, which is write the header section. So, yeah, okay, this I'm remembering now why I don't usually click these mark as complete, because now that we've gotten into it, most of this will be how to pass the stage and then run tests. So step one is implement your solution. Head over to your IDE and implement your solution. Okay. And then here's how you run your tests. Worth mentioning, there's also a Codecrafter CLI that may be nice to use too. I like the Git approach, but you can do either. So our task is down here. All communications in the DNS protocol are carried in a single format called a message. Each message consists of 5 sections: header, question, answer, authority, and an additional space. In this stage, we'll focus on the header section. We'll look at the other sections in later stages. So the header looks like this. So we have a header section structure. It contains the following fields. We've also included the values that the tester expects in these stages. So you can see here, we have a packet identifier. It's 16 bits. It's a randomly assigned ID to query packets. Query response indicator, 1 for a reply, 0 for a question. Opcode, 4 bits, specifies the kind of query in the message. Authoritative answer, if the responding server owns the domain that's queried, i.e. it's the authoritative server for that. Truncation, so if the message is larger than 512 bytes, that's our limit that we just talked about. It's always 0 in UDP responses. Recursion desired, sender sets this to 1 if the server should recursively resolve this query, 0 otherwise. Recursion available, the server sets this to 1 to indicate that recursion is available. Whether it's reserved, we can go through these. I will continue to go through them. We're almost finished at this point. The response code is indicating the status of the response. Question count, number of questions in the question section, number of records in the answer section, number of records in the authority section, and then number of records in the additional section. So the expected value for our test stage is a lot of zeros, a 1 and a 1, 2, 3, and 4. So what we can end up doing here is we can essentially hard code something past this stage, which I don't necessarily think is a bad idea. If we do that, we'll have to refactor as we go because that won't scale. But I think that will get us through this stage pretty quickly, so that might be the approach that we take. The header section's always 12 bytes long. Integers are encoded in big Indian format. That is important. We will end up using the big Indian package for that at some point. You can read more about the full DNS packet format on Wikipedia or in RFC 1035. This link is a good tutorial to walk through the DNS packet format in detail. Okay. Just like in the previous stage, it'll execute it like this. Some people, you can comment on these too. Some people give you comments on how to test them without actually running through like the Codecrafters bit. But all we need to do at this point is we need to respond with that header section. So we can make a little cheeky approach here. So we know we're working with bytes. So we can do a byte of 4. We can do a byte of, byte of 210 in our case. A byte of 128, and then a bunch of zeros. So 1, 2, 3, 4. Let me just double check that here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, I think we just want 9 here. Let me make sure. 4, 5. Okay. Okay, and these values here, so it's literally a byte of 4, a byte of 210, a byte of 128. All right, let's give this a submission. So get status, get add, get commit. This will be step 2, I believe. Give this a push. And let the test run. So one thing worth mentioning too, you can kind of see this down below, but the tests in the running will also show up in the browser should you prefer to look at it that way. Okay, so we have our mock header that we're just returning. It's kind of hard-coded right now, but it is what it is. So let's mark this stage as complete and then move on to the next one. Okay, cool. So for this one, we are going to extend our DNS server to respond with the question section, the second section of a DNS message. The question section contains a list of questions, usually just one, that the sender wants to ask the receiver. This section is present in both query and reply packets. Each question has the following structure. So it has a name, which is a domain name, represented as a sequence of labels. More on this below. Type, it's a 2-byte int. The type of record, 1 for an A record, 5 for a CNAME record, etc. There's a full list here. Again, I think we only end up supporting A's at this point, but it shouldn't be too different to support CNAME or so on and so forth. The class here, it's a 2-byte int. It's usually set to 1. More information on that here. I actually don't know what the class is. The following class mnemonics and values are defined. N1, the internet. CSNet, obsolete, only used for some examples and obsolete RFCs. 3, the chaos class. I don't know what that is. And then Hesiod. I'm unfamiliar with, honestly, all of these. But I think for our example, we are just doing the internet. RFC section 4.1.2 of the RFC covers the question section, format, and detail. Section 3.2 has more on type and class. Okay, domain name encoding. Domain names in DNS packets are encoded as a sequence of labels. Labels are encoded as length content, where length is a single byte that specifies the length of the label, and content is the actual content of the label. This sequence of labels is terminated by a null byte, like so. So you can see how Google's encoded here. So here's the length. So we have, 6? Google. Yep, that's 6. 3, com. And then there's our null byte. And here's the equivalent in hex. So, oh yeah, literally, they just broke it down right here too. So that's exactly the same breakdown that I was going through. So there's the first label, single byte, it's the length of the label, it's 6. There's the 6 characters. Same thing with com, and then the null byte that terminates the domain name. So just like before, the tester will execute your program like this. It'll then send a UDP packet containing a DNS query to port 2053. Your program will need to respond with a DNS reply packet that contains the question section described above, along with the header section from the previous stage. Here are the expected values. So you can see Codecrafters IO. followed by a null byte. That's Codecrafters IO encoded as a label sequence. 1 encoded as a 2-byte big Indian int. And then the class is 1 encoded as a 2-byte big Indian int. Make sure to update the QD count field in the header section accordingly, and remember to set the ID to 1234. Okay. So this is going to be a little bit more involved than the last one. So I'm going to do a couple things. At the very top, we're going to go ahead and define a type, if I can type query struct. And I'm going to make this a little bigger, not that much, and close this out. We'll be doing, I think, everything in one file for the most part. So we're going to have a header, and that's going to be of type header. And then we're also going to have a question, which is going to be of type question. We need to be able to encode this. So we have a query. We're going to have an encode method, and it's going to return a byte slice. And let's make some assumptions here. Q.header.encode. And, sorry, that'll be header bytes. And then question bytes will be something like q.question.encode. And then we're going to return append header bytes, question bytes. So something like that. This header type doesn't exist yet, neither does the question type. So we'll have to create that as well. Okay, so let's go ahead and define that header type. So type header struct. It's going to be an ID. It'll be a uint16. And this is where we're gonna move away from that hard-coded header that we did in the last step, because it's not going to scale for us at this point. So we have QR, which is going to be a Boolean. We have opcode, which is going to be a uint8. And then we have AA, which is going to be a bool. We have TC, which is going to be a bool. And these map to those header values that we just went over in the last one. So we have RD, which is going to be a bool. And then we have RA, which is going to be a bool. Z, which is going to be a uint8. And I wish we had that information on hand just to make sure that these types are right. I'm trying to do them from memory, and we'll see how it goes. So we have rcode, which is going to be a uint8. We have qd count, which is going to be a uint16. An count, which is going to be a uint16. NS count, yeah, uint16. And then our last one is the AR count, which is also going to be a uint16. I think that should cover it. Okay, so let's go ahead and define our header encoding function. So we have a header here like so. We know that we need to be able to encode it because we're depending on that in the query encode method. So what we're doing here is essentially going to be taking the header and doing a little bit of bitwise logic. I'll be very transparent. I'm not great at explaining bit shifts and things of that nature. Bear with me on that part. We'll get through it, and then if you have questions, I guess leave them as a comment, and I'll try my best to follow up and explain how this stuff works. I've had to look this up before because bitwise math has always been something that I've struggled with. So yeah, let's see if I can remember what the maths look like. So we have flags, and essentially our flags, we're going to be bitwise manipulating everything into this flags. So it's going to be a uint16. Remember that Go has sensible default, so we get a sensible default value for flags, even though it's not defined with a value. So we know that if our header has a QR, which is not a QR code, but it is let's go back here and double check. So a query response indicator. Then we want our flags to be bit shifted like so. We also know that we need to bit shift again. uint16h opcode. We're going to take the opcode from the header. And then shift that with 11. And sorry, I do have some notes that I'm referring to for this part. If header.aa, so AA is the authoritative answer here. Some more flags manipulation, like so. If header.tc, and we'll kind of repeat this pattern. In fact, I'm going to just copy and paste this because we'll do this for AA, we'll do this for TC, we'll do this for RD, and we'll do this for RA. So we did AA, so let's do TC, but the number that we're shifting by is going to be different. So in our case, this one will be 9, the next one will be 8, the last one will be 7, and then TC, RD, RA. And again, if you are confused what those are, TC is truncation, RD is recursion desired, RA is recursion available, and then TCAA, authoritative answer, is up here. So we're getting close to being done with them, but we have a couple more that we need to go through. So we have flags, and we're going to do uint16 header.z and OX7 shifted by 4. And finally, flags uint16 header.rcode. And we don't need to shift this one, but we do need to, oh my God, what is the, oops, bitwise ampersand. What is that called? Just a bitwise and. Okay, bitwise and instead. If you are, I'm not sure if this is a great source or not for bitwise math and bit manipulation. Actually, this does look pretty good. So if you are confused on this stuff, this might be something to go through. Again, unfortunately, I'm not a master at it. I don't know it well enough to properly explain it. And I'm afraid that I may do more harm than good trying to explain it. But if you're interested in that, it is something that you do need to learn how to do for this challenge. In the simplest sense, you can copy what I have. But as you're going and building this out on your own, like you unfortunately or fortunately have to have a bit of an understanding how that works to build something in the DNS space. So something to learn, either learn how to do it or learn enough to piece together a solution, kind of like what I've done. Okay, so we're not finished with this yet. I think we are finished with bitwise stuff at this point, but we need to actually make a buffer to store this in. So this is going to be bytes. It's going to be a length of 12. Why 12? Because if we look back here at the question section, I think it tells us that it is 12. Actually, sorry, the header section. Yeah, the header section is always 12 bytes long. So we're essentially doing bitwise manipulation to build this header section and fit everything into 12 bytes. So I mentioned doing things with Big Indian earlier. We're going to do that now. So there's a binary package that we can pull in. I'm actually curious what this is. Not what we want, but interesting that it suggested that. So we can do binary.bigindian.put uint16. We want our buff. We need to give it locations. So there's our locations in that slice. And then we need to put the appropriate value in there. So the very first one is ID. And again, if you're curious what these values are and how they map, that would be in the previous section on writing the header section. So we have the ID. We essentially have all of our flags that we're going to put in there, our QD count, our AN count, etc. So let's do the same thing. So we have binary dot big Indian dot put uint16. This will be buff, and we'll do 2 to 4, and we want to put our flags. We're going to do the same thing again. Actually, is there a... I don't remember what the hotkey is in VS Code to duplicate a line is, but I think we'll want to do this 6 times total. So we'll go 4 to 6, and instead of flags, we want H, so this is header, and we want our QD count. Next, we'll want our AN count, and it's important to update the subslice here, or the indices in that slice. So from 4 to 6 was previous, we want 6 to 8 this time, 8 to 10 the next time, and then 10 to 12 the final time. And then we still need to update these last two, so we want header NS count, and then the last one is header.AR count. And again, if you are curious how those map, you can see how those are used here and how that is built. Yeah, I think that's mostly it. Let me talk through one thing that's important. So if we look at this, so we have all these fields, right? We have the packet identifier, the query response code, the opcode, all of that stuff. So we're working with bits. These right here, the authoritative answer, the truncation, recursion desired, recursion available, that type of stuff. The reason we're doing bitwise operations, we're working with essentially a single bit, and we're building like a flag set with bits to indicate what is being used. So if you see that here, 0 and 2 is the ID. So right here, 2 to 4 is going to be the flags. So that is essentially everything up until the QD count. So all of this. So we are flagging that together, and that is essentially giving us the value that we put into the buffer at that spot. We have our QD count, which is next, our AN count, NS count, and our AR count, which are captured right here. So the last thing we have to do for this function is return that buff. Cannot use buff variable type byte, byte slice as a byte return value. I'm missing, this needs to be a byte slice, not a byte. Okay, cool. We have an error somewhere. Oh yeah, question's not defined. So let's define question. I was confused why my formatting wasn't working, and it would be because the question struct is undefined. Okay, so this is going to have a name. It's going to be a string, something like google.com. It's going to have a Q type, which we talked about just a moment ago. It's going to be a uint16, and we have a Q class, which is also going to be a uint16. I said just a moment ago, it's actually been a little bit since we've talked about them at this point, but yeah, if you want more information on those, you can find it here. So type is right here, class is right here. Again, I think we're working with just a record, so the type will always be 1 in our case, and class will always be 1 as well. But for simplicity's sake, not simplicity's sake, for posterity's sake, we're going to go ahead and build like a full question struct. We're also going to encode that question. So we need an encode method, just like we did previously. So this will be a byte slice that we're returning. We're going to create a buffer of bytes. I probably need to say var, not bar. And then for each label in our range, and we're going to do strings.split sequence. If you haven't seen split sequence yet, this gives you an iterator, which is kind of cool. So you're not allocating any extra memory for the return value if you were to split. We're going to split the name on the dot. So for example, we'll have something like, google.com, like I have up here, and we're going to split that. This is a for, so we actually need to do stuff with it. So we're going to say buff, and we're going to append buff. We want our byte, we want our length, and then we want our label. So this is going to give us, again, taking the google.com example, I think they have the encoding here. Yep. So that would be something like this. And this part right here is going to give us this, the 06. Now we actually need to append the label itself. So we're going to append. We want bytes. We want label. And we want to spread that. Okay, not sure how I got an extra Q there on the byte type, so let's fix that right quick, and then let's continue. We need to do a null terminator, right? That was mentioned here as well, or a null byte. Null terminator sounds intense, like a Hollywood movie, but null byte. So we have our 0, 0 right here that we need to append. So what we're going to do here is, now that we've gone through our string that we're encoding, let's do append buff, and then there's our 0 byte. This is essentially the terminator. QType and QClass will be next. So we have QType, which is going to be make. It's going to be byte, type 2, QClass, make, byte, 2, binary, big Indian dot append, not append, sorry, we actually want put uint 16, QType, and then it'll be q dot QType. And then the same thing down here, binary, big Indian, put uint 16, Q class, Q dot Q class. We need to finally append these into our bigger buffer. So we can do buff, append, buff, QType, dot, 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 buff, append, buff, Q class, dot, dot, dot. Perfect. Finally, return our buffer. Okay. Whew. We have our encoding going. This feels pretty good, I guess. What we need to do now is actually use these types. So we're going to come back down to our main method, and we're going to clean all of this up as soon as I make sure that... What's the issue here? Cannot use question bytes variable of type byte slice. I think we just need to spread that. Yeah, okay. All right, cool. Yeah, so let's come back down here to where we hard-coded our our response, right? Create our empty response. And instead, we have our received byte. So what we're going to do is create like a header, which is going to be header ID 1234, QR true, opcode is 0. Where are these values coming from? They're mentioned again in the previous section. So these are the header values. These are the default values that we want. So you can see 1, 2, 3, 4, 1, 0, 0, 0. Some of these are Booleans, so the zeros are falses and ones are trues. So for example, AAA is false instead of 0. TC is false. RD is false. RA false. And I'm just looking over here as we go to kind of make sure I'm doing these correctly. Z is 0. Our code is our next one, which is going to be 0. Our QD count is going to be 1 now because we have a question. Sorry, it's QD count. We have a question that we're receiving. We have an answer that we're providing. So our answer count is going to be 1. Our NS count is still going to be 0, and our AR count is still going to be 0 as well. More information on that. I think they mentioned updating the values here. Yeah, remember to update the QD count field in the header section accordingly, and remember to set the ID to 1, 2, 3, 4. So should be good there. So this is our header. We have our header now. We need to create our question. This one will be a little quicker. So question, it's going to be type question. The name, we're hard coding it to codecrafters.io. The Q type is 1, and the Q class is 1. Finally, we have our query type, which is going to be a query. Let me type that right. And our header is going to be header. And our question is going to be question. Okay, so this is our DNS packet. We're actually finally getting there. So we have our query packet here, and we have our header section, and we have our question section. So for now, I think this should cover it. We will need to support multiple questions at some point, but we'll get to that when the time comes. and it shouldn't be too bad to support. So now we can take our hard-coded byte slice here and change this to query.encode. Looks pretty good. Anything else? I don't think so. Let's let Codecrafters test this for us. So I make sure that was the only thing. Git commit stage 3. Let's give it a shot. And while this runs, I'm going to take a drink of my beverage because my throat is getting dry from talking for 40 minutes straight. Hey, our test passed. Excellent. We're actually like almost halfway done, which is pretty good, although we have a pretty hard part ahead of us. So we're going to mark the stage as complete. Somewhere I could have swore that you were able to see the difficult stages. Like it would tell you like this stage is more difficult than the other. I don't know where you would see that. Oh, this one says easy. What was writing the question section? That was medium. We'd expect a proficient developer to take 30 minutes to 1 hour to complete this stage. Okay, cool. Curious, just exploring. Okay, we have a hard one. This one is the one that they think will take more than an hour. Let's hope not. Okay. So yeah, write the answer section. In this stage, you'll extend the DNS server to respond with the answer section, the third section of the DNS message. So the answer section contains a list of resource records, RRs, which are the answers to the questions asked in the question section. So we're going to have a couple different things we need to do. We're going to create another type, and it's going to represent this. So we have a name. It's a label sequence. We talked about label sequences previously. We have a type as a 2-bit integer, 1 for A record, 5 for CNAME, etc. We've talked about that. Class, we've also talked about that. It's going to have a TTL, so time to live. The duration in seconds to record can be cached before requerying. It's going to have a length for the RData field types. So there's RD length right here, although it'll just be called length. And then we have data, which is a variable which data specifies data specific to the record type. You want to learn more? Section 3.2.1 of the RFC covers the answer section format in detail. I'm kind of skipping over these, but the first time I started looking at this challenge, I read through most of these. I would strongly recommend doing that too if you have the time or want to make the time. It will hopefully make a lot of this make more sense as you go, and I would strongly encourage it. In this stage, we'll only deal with the A record type, which maps a domain name to an IPv4 address. The RData field in an A record type is a 4-byte integer representing the IPv4 address. Just like before, sends a UDP packet. It needs to respond with a DNS packet that contains a header section, we've already done, question section, we've already done, and answer section, new in this stage. Your answer should contain a single resource record with the following values. So Codecrafters IO followed by a null byte, the type, the class, the TTL, length, and data that we just talked about. Make sure to update the AN count field. I actually think we did that in the last one, so I don't think we need to. I guess the test didn't check that value, but yeah. So let's get back to it. So we're going to hop all the way back up to our query. We're going to add a new type. This is going to be answers. And I'm going to go ahead and make this a slice for resource record. We'll come back and update question at some point. But for now, I think both question and answers are actually supposed to be slices or arrays or whatever list type your language has. So we're going to update our encode method to handle these new answers. So we'll have something like answer bytes. And I like starting from when we're introducing a new type like this, I like starting from the thing that's going to call it. So I can start to kind of think through what that interface will look like. So in our case, we're going to create a byte slice here like so. For answer range, q.answers, something like that. Answer bytes is going to be append answer bytes. And then we need to do like answer.encode. And since that's going to return a byte slice, we need to spread that as well. What else we got? We essentially need to take the header bytes and the question by bytes and the answer bytes and append them all together. I'm just going to use an intermediate variable for that. I'm going to call it HQ for header questions, and we'll do append header bytes, question bytes, and then what we'll do is down here, we'll change this to HQ, and then change this from question bytes to answer bytes. This maybe isn't the cleanest solution, but I think it should cover it. We do need to make our resource record struct as well. I'm kind of throwing these all over the place. You might want to organize yours better, but hopefully you're also not trying to knock this out in a YouTube video within a couple hours. So you hopefully have a little bit more time to think through proper placement and folder structure and all that stuff. So we're going to create a resource record struct. It's going to have a name. It's going to be a string. It's going to have a type. Type's going to be uint16. Get familiar with uint16 if you haven't yet already. We're using it a lot. We're also going to have a class, which is going to be uint16. However, we're going to break what I just said and do a TTL, which is going to be a uint32. And then we're going to have our data, which is going to be a byte. And remember, we also have that length, right? This length. It corresponds to the length of the RData field. There's no reason to have a separate field for it. We'll just encode the length when we encode, or we'll synthesize the length when we start to encode the RData piece. Okay, so let's get to this part. So we have a func. We're gonna have a resource record. We need to call encode. We're gonna return a byte slice. We're gonna start with a buff, and it's gonna be a byte slice. Let's do labels string split. Actually, we probably should use the sequence here because we're going to iterate over it too. So let's take that approach. So let's say for label in range strings split sequence, and the string will be resource record.name. Yeah, take the same approach we did previously. I'm not sure why I wouldn't actually. So this will actually be really similar, and if we really wanted to, we could probably break this out to a function, which might not be a bad idea, but for now, let's just append buff byte length, and then it'll be label. And then we need to go to the next line and do another append. So we're appending buff, and we want byte label spread. And that's basically the same thing we did previously for names, the labeled strings, I think is what they're called. And then we're going to append buff, and we also need that null byte. Okay, so we need to handle our type. We're also going to do a pretty similar pattern here. So thinking about that, that might be a fun little exercise. I probably won't do that since this video is going to be pretty long as it is, but you could totally refactor this and really cut down on the code reuse. So big Indian, put uint 16, sorry, big Indian, put uint 16, not append, t, and this will be resource record type, and then we need to append it. So again, this is going to be a pattern, and we're going to copy and paste. I'm going to put a little bit more space there so I don't forget. So we also need to do the same with C, and then this will be C and RR class, and then this becomes C as well. And then down here, this will be TTL. This will be the time to live, and this will be TTL and time to live. Okay. Feeling decent about that. Let's go do RD length. Actually, it's going to be the exact same thing, exact same pattern, I should say. So it'll be RD length, and then this will be slightly different. Sorry, I'm just thinking it shouldn't be the exact same because TTL actually should be put uint 32, not uint 16. So, and we know it's a, yeah, okay, much better. almost tripped up on the copy and paste. So what we have down here is our D length is going to be RD length. And then what we're working with is uint16 length rr.rdata. That should cover it. And then we need to take RD length, spread that on the buffer. And really what we're doing is we're essentially making these little micro buffers, and then we're putting things in them, and then we're appending that micro buffer to the larger buffer. Sounds very memory inefficient. It does seem that way to me as well, but we're working on a forward solution, and you can always come back and clean things up. In fact, I really would encourage it too. It seems like a great way to really cement the knowledge that we are working through together. So we're going to append our data, and then we're going to return buff. And now we have encoding for our answer. So thankfully, we still have hard-coded values at this point. So what we can do here is we can come right after question and create answer. And we'll have something like answer. Sorry, it's not answer. It's actually resource record. Tripped myself up on that. And we need to give it a name. It says Codecrafters is what we want for the expected value. So the name will be codecrafters.io. The type is 1. The class is 1. The TTL is any value, for example, 60. You got it. 60 it is. And then the R data is going to be a byte slice and 8888. You got it. Now we need to go update our query. So we have answers, and this is going to be a slice of resource records. And we only have one for now, which is going to be answer. Whew, okay, feels pretty good. Let's give that a shot. And then if all is good, we'll be able to move on to the parsing part, which will be the most fun. Okay, so this is stage 4. Give this a push. Nice, we panicked. Runtime error, index out of range 3 with length of 2. Looks like we have a binary put, maybe some encoding issues going on. Main.go 52, let's go take a look. So we got 52 somewhere up here. So we are looking at our TTL, and we aren't giving it enough space. This should be 4, not 2. I knew I missed something else on the TTL piece. So let's give this another go. I'm just going to commit the same commit message again since it is stage 4. Give that a commit, give that a push. Nice. Okay, tested past that time. Excellent. Small little typo, but those are the ones that are often the most dangerous. Okay, I'm going to mark this stage as complete. We'll move on to parsing the header section. This one is considered to be very hard. Again, I have a little bit of notes just looking at this ahead of time to help make this hopefully not as bad, but let's get into it. Up until now, we were ignoring the contents of the DNS packet that we received and hardcoding 1234 as the ID in the response. In this stage, you'll actually have to parse the DNS packet that you receive and respond with the same ID in the response. You'll also need to set some other fields in the header section. Okay, cool. So we're now at the point where we actually care about what is being sent in. So up to this point, we've just been writing stuff back anytime we get a packet. And now what we need to do is actually look at the incoming packet, parse it into essentially a header section, and then return things on the header section. We'll do the same thing with the question section after that, and then we'll talk about compressed packets, and then finally set up the forwarding server, which actually will be one of the easier parts, I think. We will probably introduce a new file for this one. So here's information on what we need to respond with. Hopefully these fields look pretty normal at this point, and you're not confused by any of them. They're all things we've seen before. But the expected values, we need to mimic the packet identifier, mimic the opcode, mimic the RD value. 0, no error if opcode is 0, standard query, else 4, not implemented, and then any valid value for the rest of these. You shouldn't need to hardcode 1, 2, 3, 4 since the tester sends 1, 2, 3, 4 in the ID of the previous stages. Your code should automatically pass the previous stages as well. Okay, cool. Yeah, let's get to it. So in our main method down here where we're creating this empty response, we have this data, right? We're receiving some data, but we're not actually doing anything with it. So again, I like to think about how we're going to use this before we actually implement it. So I'm going to say that we're going to get a message and probably an error, and we're going to call parse message, and then we're going to pass in like, let's do the buff and the size. And we'll just work on the byte slice directly instead of like the string value, which will allow us to remove the string value once we are done with it. But I'll keep it in for debugging purposes. There's a weird like exception to the normal flow here, which is this. So the response code is going to be 0 if the opcode is 0, else it'll be 4. So let's just go ahead and like handle that too. That's not really related to parsing. It's related to this problem. So yeah, something like this. Response code is equal to 4. And then we'll need to set these values, right? So we'll have like message.header.id. And this message is also going to more or less be a query. It'll be pretty close to a query, I guess. And it'll have message.header.opcode. And then down here for RD, I think. Yeah, mimic the RD value. Message.header.rd. Sorry, RD. And then our code will be response code. Makes sense to me. Okay, so we actually need to write that parse message function, right? And this is where the meat and potatoes of this will really be, I guess. So yeah, let's find a home for that. I'm just going to put it above the main method, I guess. This definitely seems like right here would be the spot where you maybe like want to break out another function, or sorry, another file. But yeah, parse message data byte. Sorry, the return type is going to be a pointer to a message or an error. We need to define that message type, right? Because it's almost a query, but not a query. So type message struct header. It'll be a pointer to a header. Questions, a slice, question, answers. And these are all resource records, so we'll do resource record. Authorities, I think, will also just be a resource record. I don't see why it wouldn't. And then additionals. Okay, so that's maybe what our message might look like. So yeah. Okay, so we want to get the header from a message. So parse header data. If error is not equal to nil, return nil error. I think what we'll do here at this point, it might just be easier to just go ahead and start working on like a more comprehensive parser that kind of covers just about every piece of what we need. So I think what I'm going to do is I'm also going to define a type down here called type parser, and it's going to be a struct. It's going to have that data. It's going to be a byte slice and an offset, maybe. Seems good. So the parser is going to need to do a couple things. We'll need to read a byte. So that would be something like the byte is going to be p.data, p.offset. and then we'll increment p.off, and then we'll just return b. So that should handle reading a byte. We need to be able to read uint16s. We also have the TTL, which could be a uint32, so we need to support that. So we'll do function p parser read uint16. My goodness, if I can type correctly, uint16. So we're going to have a value in v, binary, big endian, uint16, and it'll be p.data. And again, we have the same thing where we want p.off. And then we'll do p.off plus equal 2, since we're working with uint16s. And then we'll return v. I'm going to copy this. We're going to do the exact same thing for uint32s, and then we'll just update a couple of the values that need to be updated. So in our case, read int32, it'll be, yep, this still looks good. This needs to change to uint32. The offset goes up by 4, and then this needs to become a 32-bit int. Okay. So we have some basic parser pieces that we're working with here. This approach is maybe a little all over the place. Bear with me. We'll see how it comes together. I think it should turn out okay. So we're going to also parse a header. And we need our data, which is going to be a byte slice. And we're going to return a header and an error. So if the length of our data is less than 12, it's not valid. So we'll go ahead and handle that case. So we'll return nil font error f too short. Never remember the formatting. It's W. Okay, cool. There's actually not an error to wrap, so we'll just say too short. That's not helpful. Too short for DNS header. How about something a little more helpful? Okay, cool. If that's not the case, we can go ahead and create our header. So we'll have a header like so. We need to set some fields, like ID is going to be binary.bigendian. It'll be a uint16, and that's going to be data 02. Flags, binary, big Indian, uint16. I'm actually starting to wonder how much of the previous parser stuff we'll actually need here. So we may change our approach a little bit too. Okay, so we're getting our flags, right? And we talked a little bit about our flags and the bit shifting. So basically what we're going to need to do is shift everything out into normal values. So we'll do h.qr, and that's going to be flags shifted bitwise and 1 is equal to 1. Opcode is going to be similar, so it'll be a uint8. And we'll take flags shifted into 11 and OXF. Same thing with AA. And these actually should be really straightforward. It'll be 10 and 1 is equal to 1. And we should be able to just copy and paste this a couple of times and change these from AA to, this will be TC, this will be RD, this will be RA. And 10 becomes 9, becomes 8, becomes 7. Now we need to handle the Z case, so h.z is equal to uint8, if I can type that. Flags, and then we want to shift 4 and OX7. h.rcode uint8, and that'll just be flags with a bitwise and like so. Whew, almost finished. We just have the QD count, which is actually going to be straightforward compared to those. So this will just be binary dot big Indian U16, and it'll be data 4.6. We're going to copy and paste this a couple of times because it's more or less the same approach for the rest of these. So this goes from 4 to 6 to 6 to 8, 8 to 10, 10 to 12. And then we need to update the actual values here that we're storing them in. So this will be AN count. This will be NS count. And this will be AR count. Okay. Yeah, we're just going to keep going with the parser. So we actually might knock out the question section as well. We've talked about questions already. So hopefully there's not anything too confusing that would be skipped over by that. And we'll even see. I may not end up doing that, but I feel like I should just go ahead and implement that while we're on a roll with the parser. So yeah, let's go ahead and return our values here before I forget. So this will be return h nil. We're going to create a func parser. This will be read. Oh my goodness, read question. And the return type will be a pointer to a question, error, name, error, and it'll be p.readName. We haven't built readName yet, so we'll need to do that. Names are tricky, right? Because they are, I've already forgotten the term for it. It's in here somewhere. Label sequence. So it's not just like we have to handle the case where it's a label sequence, which they will always be a label sequence. So we need to handle that appropriately. So we have our read. Let me type question properly. So read question. So we're going to read that name, which we need to implement. If error is not equal to nil, we'll just return nil error. And then if we don't hit that case, we should just be able to return question, name, qtype, p.read, uint16, qclass. Yeah, okay. This is why we need the read uint16s. And then nil. We'll do the same thing for reading a resource. So func p parser read resource name. Sorry, read resource record. It's not a name. It's the whole record. The type we're going to return here is a pointer to a resource record or an error. And then yeah, it's basically going to be the same at the start because we need to read the name. So it'll be read name. If error is not equal to nil, return nil error, RR, ampersand resource record. So name will be name, type will be p.read int u16, class will be p.read uint16, and then the TTL is a 32, so we will use read uint32 instead. We do need to get the length of the data, right? The R data. So we can do something like R data length, and it's a uint16. Oh, oops. Not sure how I did that. uint16. And then this gets a little tricky because we essentially need to make sure that we're not truncating our R data. So if p.off plus int read length, basically making sure that it still is within the remaining space, like so, making sure that it's not greater than the length of p data. If it is, we want to return nil, and then error f, truncated R data, something like that. Otherwise, we can continue and say rr.rdata is equal to p.data. We want the p.offset to the p.off plus an int formatting of the length. Oh, there we go. And then finally, we need to adjust our offset for that on our parser. And then we can return RR nil. Okay, this feels pretty good. We still actually have the hardest part ahead of us, which is the name, right? So I'm going to skip ahead just a little bit. We're working on parsing the header section. We're actually going to get parsing the question section from this, or pretty close to this. The thing I want to talk about is the compressed packet. So in this stage, we'll parse the DNS question section, which has compressed question label sequences. You'll be sent multiple values in the question section, and you'll have to parse the queries and respond in the same question section. No need for compression. The key thing here is that the questions can have compressed label sequences. And then what they expect back is the uncompressed questions and answers. So you don't need to compress your response. This section of the RFC covers how compression works. I'm going to load this and take a sip really quick to wet my dry throat. Okay. In order to reduce the size of messages, the domain system utilizes a compression scheme which eliminates the repetition of domain names in a message. In this scheme, an entire domain name or a list of labels at the end of the domain name is replaced with a pointer to a prior occurrence of the same name. The pointer takes the form of a 2-octet sequence. So you can see here. The first 2 bits are ones. This allows the pointer to be distinguished from a label, since the label must begin with 2 0 bits, because labels are restricted to 63 octets or less. More information about 10 and 01. The short and sweet here is that essentially the compression scheme allows a domain name and a message to be represented either as a sequence of labels ending in a 0 octet or a pointer, or a sequence of labels ending in a pointer. The reason I'm mentioning this now is that we're going to go ahead and build the compression in. If you would like to learn more about it, this is arguably one of the more interesting parts. I would strongly recommend reading this RFC. So just, yeah, that's fine. My throat's too dry to go through all of this at this point. So what we're going to do is we're going to build that read name function that we've talked about on our parser, and we're just going to go ahead and support compression from the get-go. Because it would be easier to build it with compression in mind than try to retrofit it on later. So let's do that. So we have P, we have our parser, we have our read name function. It's going to return a string or an error. I guess and an error, technically. We have our labels, which is going to be a slice of string. We have our start, which is going to be our existing offset, and then we need to know if we're jumping, and jumping is essentially what will happen when we have those compressed values. So if we have a pointer and we need to jump, that's going to be our indicator of whether we're jumping or not. Okay. Now's also a very good time to caveat that outside of this challenge and a little bit of research for this, I'm not an expert on DNS. So if I've said something wrong, and it feels like I might have just said something wrong right there talking about jumping and how that works, please feel free to correct me. I am always open to constructive criticism and helping myself grow as well. So if that feels off and you are an expert or know someone who is an expert or just know how to find the right answer, feel free to let me know in the comments below. I do always appreciate it. Okay, so we essentially need to check and make sure of a couple of things. So we're going to do an if p.off is greater than or equal to the length of p.data. And again, we have essentially another case where this is out of bounds. So what we're going to do here is return an empty string and then fumpt error f, something like name out of range. Something like that. Seems good. Length will be an int. This will be p.data, p.off. That's going to give us our length. And then we need to increment p.off. So it'll be p.off. It's easier said than typed, I guess. And then now we want to check if length and OXCO is equal to OXCO. This is going to handle our compression here. Let me space that out. I don't know why I typed it that way. Then we essentially need to do another check, right? So we can check length p.data because this could be different when we're handling compression. So in this case, we would have like fumped error f. This would be a sign of a truncated pointer. We have our pointer, which is going to be, this is going to be length and OX3F. And then we're going to shift that 8. And then do a bitwise OR int p.data p.off. I think that's correct. We'll struggling to talk. We will find out once we run our git push, and Codecrafters tells us whether we are failing or not. Okay, so if that's what happens, we actually have a sub parser, which is kind of interesting. So what we're going to do is we're going to create a sub parser. The data is going to be p.data. The offset is going to be the pointer. And essentially, we have a pointer. We need to go to a certain space. Let me fix this before I forget. And yeah, go to that space and then parse what needs to be parsed for the name. So now that we're here, we'll do name, error, and this is going to be the sub parser. So we'll do sub.readName. If error is not equal to nil, we'll return our error. Labels, yep, okay. Append name. So we should have our name from our sub parser. If we did not jump, then the start becomes p.off. Then we set jumped to true. Yeah, I just misspoke, sorry. If we have not jumped at this point, we'll go ahead and update the start to p.off, and then we'll set jumped to true. Next, we need to break. And then down here, we can check if length is equal to 0. Then we have, this will be the case where we have our terminator. Terminator case. If p.off plus length is greater than the length of p.data, we yet again have a case where we would out of bounds. So we need to handle error f, truncated label. Otherwise, we can say label string p.data. It'll be p.offset sliced to p.off plus length. And then p.off plus equal length. Labels, append, labels, label. Okay, whew. Actually, I don't know how I feel about that. I feel like we will let Codecrafters tell us if we're correct. But I think, just again, conferring with notes that I have, I think that should cover it. If we have jumped, then p.offset needs to go back to the start. Finally, return strings.join labels. Nil. Okay, cool. Okay, so let's just talk through this again really quick because I feel like this could be confusing. Really, the key thing to keep in mind here is the jumping, right? So if we find a compressed packet, then what we need to do is we're essentially going to do some jumping and try to figure out with a sub parser. So if we have a compressed packet, let's make sure that we're not going to go out of bounds. And then we get our pointer value, we up our offset, and then we create a sub parser. That sub parser it's a parser just like the one we're currently in, but it's just going to focus on that new offset value. And then we're going to call read name. So that's going to give us a name, hopefully, or else it'll give us an error. And then we append that name to our labels. If we haven't jumped yet, we set our start equal to our offset value, and then we set jumped equal to true. Then we break. So we're doing that in a for loop up here, right? So additionally, if our length is 0, we end up in a terminator case. So this is the null terminator. So we're going to go ahead and break. If, again, this is a bounds check. So if we're out of bounds again, we return truncated label. Otherwise, we grab our label, we increment our offset by the length of that label, and then we append it. If we did jump, we have to go back. Like if we're here and we jump over to here, we've left all of these values out. So what we need to do is we need to we need to reset our offset to the starting offset value before our jump. Finally, we just do strings join and return that. There's nothing crazy going on there. Okay. This is most of what we should need for, I think, most of the parser. I guess we need to finish the parse message function that we kind of started with. So let's think through what that might look like. I think we're pretty close, and I think we'll mostly just have some patterns that we need to follow. So we're going to have a parser, and it's going to get data, and it's going to get an offset. And the offset's going to start at 12. Why does it start at 12? Where do we have 12 at where we are there? So the header section is always 12 bytes long. We are parsing the message. We've already parsed the header. We don't need to parse the header again. In fact, we specifically need to avoid trying to parse the header because it will throw off the rest of our parser. So we're offsetting it by 12. Is it not called offset? Oh, it's just called off. Okay. So we also need a message. So we're going to make a pointer to a message, and it's going to have a header, and that header is going to be H. So now what we're going to do, and thankfully we'll basically copy this a couple of times, but we're going to do a for loop while it is less than the header.qd count, so the question count, I++. Then we just need to parse that question, right? So we have a question, maybe an error. We're going to say p.read question. If error is not equal to nil, we'll return nil error. And then we'll set m questions append, and we have Q, our new question. That's essentially the approach we're going to take for the rest of these too. So we're going to do another loop. So it'll be for I is equal to 0, while I is less than int header.answer count I++. We're going to get a resource record, maybe an error, and we're going to get that from p.read resource record. If our error is not equal to nil, we'll return nil error. And then we'll set answers, and we'll append our resource record for our answers. Authorities and additionals are essentially going to be the exact same. So I'm just going to copy and paste this so you don't have to watch me type this out again. It's not good for you. It's not good for me. Let's let those format, and then we'll change these. So instead of answer count, this will be NS count for our authorities. It'll still be a resource record, which is totally fine. The main thing here is that we're changing this to authorities. And then, oh, that's important. This also becomes authorities. And then down here, this becomes additionals. This becomes additionals. And this will be based off of the AR count. Okay. Oh, we need to return. let's actually give us a value. So we're going to return M, which is our message, and then we'll return nil at that point for the error if we make it to this point. So this feels pretty good. Have we updated our main to handle this? We have our parse message. The value of error is never used. If error is not equal to nil, return. What is this return? Is this our main method? Yeah, I guess we could panic. We could log. I don't know. We got a couple options. Yeah, something like that, I guess. And then we're using these values that we've got. So I think at this point, we should be good to commit this. So I'm just going to say parser stages, because this actually might knock out more than one in our case. Actually, it won't knock out more than one because we're not actually updating the return type for the next sections, but that's fine. We'll get to that in just a second. Things are looking good. Yeah, test passed. Okay, awesome. So we are parsing at least the header section. So we're going to mark the stage as complete, and we'll go to the next stage. So you can see the tests are running for the next stage too, parse question section. We'll see if they pass. I don't think they will. Yeah, they failed. Okay, cool. So we can hit show logs and see why. Expected answer domain to be abc.codecrafters.io, .codecrafters.io. Looks like we're probably hard coding something. So what we can do now is read through these instructions for parsing the question section. I think we have most of the heavy lifting done for this. So yeah, I think all we need to do is update our question. Yep, look at that. And our question will become message.questions0.name. And then I don't think we have any other parser changes that we need to make. What are you doing? Let's go ahead and commit this and give this a shot. There might be some parser changes that we need to make too. So this will be parser questions. And we'll give this the old push, the old college push. Nice. Did I not save? Still got Codecrafters IO. How did we... Oh, oops. Yeah, it's literally hard-coded right here. In theory, the thing that we're answering should be the same name that was provided, right? So our resource record that we're answering, it's essentially a way to map them together. So we have our question for this domain, and we're saying this is the domain that I'm giving you an answer to. Here's the IP address. So it should just be the same. So let's give that another shot. Nice. Okay, yeah, test passed. Congrats. Excellent, excellent, excellent. Okay, so that covers the question stage. I'm a little less certain on... Okay, test failed. Let's see if we can see why. Expected answer section to have 2 entries and got 1. Oh, yeah, that seems reasonable. Okay, so we already know that the question and answer stages look like this. So there's 2 questions, and 2 answers. So the question type will always be A, the question class will always be in. Sounds good. I think we have some compression working. We might have to change it a little bit. I don't know, let's find out. But one thing we do need to do is we need to update our types for questions so that we can support multiple. Okay, so let's go ahead and take a look at that. So somewhere up here, do we not really need that read byte method? I could have swore we used that, but maybe we started to use it and we changed our mind. So we have some types here. We have our query type. Yeah, this one, right? So this needs to change from question to questions. And I think we'll actually just go ahead and change these all to pointers too. So this becomes a little different. We'll essentially, whoa, what happened there? We'll essentially do the same thing that we were doing here with answer bytes. So we'll take question bytes and encode them. Where this gets tricky too, though, is we essentially need to know those offsets. So as we're running into items in the... Yeah, I think we're actually going to have to change our compression stuff. I don't think I built this properly. Let me just try this really quick. For question in range q.questions, question bytes equals append question bytes question dot encode dot. Okay, change that, and then this should just become a byte slice. Let me just try that really quick. I'm 90% sure we're gonna have to change a fair bit of stuff here. We definitely have an error down here because this needs to be a question slice. This becomes questions. Okay, yeah, so this will, so we essentially need to generate our answers and our questions. Actually, I guess we don't need to. We don't really need to do anything with these questions, right? So we can just say that it's going to be message.questions, but we do need to build our answers. Okay, this makes more sense. So answers will be something like a slice to a pointer of resource records. And then we essentially want to generate an answer for each question. So it'll be range message.questions. Okay, answer is going to be answer question. Answers is going to be equal to append answers answer. And then down here, this will become answers. Okay, so we need to add this answer question method, I suppose. So we don't need this question. We don't need this answer anymore. Let's go ahead and trim the fat there. Let's go ahead and throw in a func answer question method. So it'll be Q. It'll be a pointer to question, pointer to a resource record. We're going to return ampersand resource record name, Q.name, type 1, class 1. And that's, again, something that is a constraint for the Codecrafters challenge. You might actually want to read those from the message or from the question. and make sure you're passing in the same thing. But for the sake of the Codecrafters one, those will always be set to 1. And I guess the address will always be set to 8888 as well. Okay, so now we have our answer question method. I'm going to commit this and push this and just see how the tests behave with this. Answer questions. Give this a push and let's take a look. DNS query failed, overflowing header size. Okay. Yeah, I'm guessing that is too long of a domain name and should be compressed. So in that case, we are having an issue with our compression, which totally makes sense. I'm not surprised, I should say. So maybe let's revisit our compression handling and our parsing and see if we can maybe simplify that a little bit. Okay, so I think what we need to do, this shows us an example, right? So essentially, like, this is probably compressed because it's long and it's reused. So in our case, I think what we need to do is we essentially need to have like a map that shows us like our jump coordinates for pointers that we need to pass along. So I'm going to, I guess, just apparently scroll around a bunch. But I'm also going to find our read name function, which is right here. And what I'm going to do is I'm going to update this to read name with jumps. And we're going to take in a map. And this is going to be a map of those jump points and whether we jumped or not. So we have a Boolean. We're still returning a string error. We do need, I'm going to essentially create like a proxy function here. It's going to take in a p parser, and it's going to be called read name, no parameters, string, error. And we're just going to return p.readName with jumps. And we're going to make map int bool. Okay, we need to like use this, right? So we're going to change some of this a bit. We've got like labels, and we're going to keep our labels. We need our original offset. So original off. This is going to be p.off. And this is going to be, essentially, we just want to know where this is for the sake of compression. For the sake of compression. I guess that's essentially the same thing as our start, but original off may be clearer. We're going to set jump to false. This will be used to track if we've followed a pointer. We have our for. This is essentially that out of bounds check. We still want to keep that. We also just want to add essentially like loop checking, right? So we can do if visited p.off. So if we've been to p.off, return thumpt.errorf compression loop detected at offset %d p.off. Honestly, that might be over engineering. This might not actually be something we need to worry too much about, but we'll find out. So we still want our checks here. OXCO, OXCO, just making sure I'm not doing anything silly. Yep, truncated pointer check. Pointer length. Okay, PTR. So, okay, length. OX3F. Okay. Bitshift 8 int p.data.off. P.off goes up. Let's add another check here. If pointer length p.data return thump.errorf pointer out of range, %d. Okay. Oh, wow. There we go. Visited original off is equal to true. Mark offset as visited. We have our sub parser. Okay. So we have our name and we're doing read name. I think we want to change this to read name with jumps. Pass in visited. And then name, error. Okay, feels good. Do our error check. Let's make sure that if, oh my gosh, if name is not equal to an empty string, then we'll do our appending. And then if we've not jumped, we can set jumped equal to true. And then we don't need that. And I'm just going to add a comment here so I don't forget. Mark that we've followed a pointer. And then one more key thing. So if we run into this break scenario, we know that we've hit a compression pointer, which compression pointer always terminates current label sequence. Okay, we still handle the length of 0, which is our terminator case. Curious if we need any additional handling here. So we have our label, p.data, p.off length. Yep, labels, append, labels. Don't need this anymore. Strings.join. I don't think so. There's a length limit to label. Okay, let's add the length limit to labels just to be safe. So if, yeah, that's fine. Sure, that's fine. We can do it there. If length is greater than 63, return empty fumpt.errorf, label too long. And then let's just give it the length so we know that in case that error bubbles its way back up. Okay, let's give this another shot. Okay, still getting an overflowing header size. Let's see what I'm missing. Okay, so looking at this, it looks like the Codecrafters output is validating the Codecrafters test is validating our output. So it actually looks like maybe our parsing is correct, but how we're handling our encoding is not. And I think maybe part of this would be that the way that we're encoding names could potentially be incorrect. So what I want to do is take a look at our encode method again for our query and just take a look at how we're approaching this and make sure that this makes sense. So I'm going to restructure some of this. It might just be easier. So this will be buff and this will be a byte slice. That way it doesn't have any opinions on how it's being used. We know that we have our header bytes, and our header bytes are going to be appended to our buffer So header bytes, yep, like so. And we need to handle our questions. I think what we need to do here is we probably want to handle an offset. So similarly to how we were doing the parsing, we have like an offset map. So let's create a map string. It'll be an int. And what we're going to do here is iterate through our questions like so. Question encode. Let's actually change the signature a little bit. Maybe let's do question.encode. And what we're going to pass in is a pointer to our buffer and then our offset map. I kind of like this pattern a little bit better. Not that it's anything substantial at this point, since I'm not even sure if this is going to be an approach that works, but we'll do answer encode. Same thing for answer. We're going to pass in a buff, and then we're going to pass in an offset map, and this will be A and S, sorry. In that case, we shouldn't need this appending. We shouldn't need this appending. And then we can return buff. And then this way, we're not essentially just like getting a bunch of sub buffers and appending buffers to buffers. It might actually be better to just have one buffer that we are using with a maximum size that we can essentially manage if we need to get to that point. So let's go take a look at question encode. And what we're going to do is modify this type so that it gets a buffer. And this will be a pointer to a byte slice, and then we get an offset map, which is going to be a map of string int, and it doesn't need to return a byte slice anymore. We don't need this buffer here. And yeah, let's actually pull some stuff out too. So we're going to create a function called encode name. So this will be encode name. It'll take a string, a buffer to a pointer, byte slice, offset map. It'll be a map string int. If name is equal to an empty string, do a pointer to a sorry, we'll do that. Buffer, append, buff 0, return. Labels, strings, split, name, split on the dot. For I is equal to 0, while I is less than the length of labels. I++. Our suffix is going to be strings.join. Oh, that's a comma. It needs to be a semicolon. Our suffix is going to be strings.join. Labels. I. Dot. If POS, okay, offset map, suffix, okay, pointer, OXCOOO, or position, make, byte slice, 2, binary.bigendian.put u16 p uint 16 pointer. Okay. Finally, let's update that buffer to append buff p return. Otherwise, we want to update our offset map. So we have our suffix here. And it's going to be the length. My goodness, it's going to be the length of that buffer. Label, labels, I, buff equals append, byte slice, length, label, Sure. And then same thing for append, byte slice, label, and spread. And then down here, pointer to buff, append, buff 0. Okay, so that gives us our encode name function. So I think this whole approach will start to change, right? So now that we've got this encode name function, what we can essentially do, we still need the queue type pieces. I guess we don't really necessarily need 2 buffers for that, but we can come here and go to encode name, queue.name, buff offset map. And we don't need to return that value there. So yeah, something like that. And then resource records are going to get the exact same treatment, I suppose. So if we go to resource records and we do our encoding up here, this will change. Encode name. This will be queue.name, buff, offset map. Haven't updated the method signature for those yet, so let's update that. So it'll be a pointer to a byte slice, and then an offset map, which is going to be a map string int. And then, sorry, this isn't queue.name. This would be resource record name. We'll have to update some of these. So bada bing. Okay. So we have our name encoding. We have some of the like compression support, I guess. Let's give this another go. I'm still not confident that this will fix all of those issues, but maybe it'll get us further, in which case we can troubleshoot some more. Let's give it a go. Nice, failed to compile. Okay. That is definitely a sign that it's not going to be working. That was just me forgetting that I need to update that return type. So let's give this another shot. We'll add, we'll commit, and then we'll give this a push. Overflow unpacking A. I'm just going to add a print line down here just to string the response and see what we get. I felt like things were moving along really, really well, and then we hit this part, and now I feel like I'm spinning my wheels. Is this the output? It does look like it's the output. That doesn't look correct. Okay, through the magic of editing, I've saved you more time than I would care to admit of watching me read through this code step by step and try to figure out what the heck was going on, or what was going wrong, I should say. 2 things. One, just make sure your AN count is set to message.questions, not message.answers. And then besides that, I came back and rewrote this encode function. It's really not that different, but I just wanted to make sure that I wasn't doing anything wrong. And at some point I was, because there's a substantial enough difference here that somewhere, somehow I have broken something, and rewriting it with that approach seemed to be a working solution. So yeah. Okay. Able to get that passed. So sorry that one took as long as it did. I was not expecting to spend that much time on it, but I guess that is why they consider it to be one of the harder ones. So our last step is adding a forwarding DNS server. This is actually pretty straightforward, thankfully. This one won't take too long. So you can see that we need to handle a flag called resolver. It gets an address, and then it'll send a UDP packet containing a DNS query to port 2053. Essentially, we take in a query, we pass it on, and then we return the response. So pretty straightforward. Honestly, it feels like this one probably should have been earlier in the flow compared to what we just ended on. But yeah, it is what it is. Okay, so let's talk through the resolver. So what we're going to do is somewhere in our main method, we've got like logs from your program will appear here. I'm just going to do address flag string. This is using the flag package. I'm going to call it resolver. The default is going to be an empty string. And then perfect. Thanks for this suggestion. That's funny. I actually turned off Copilot suggestions when we started this, and it's been that long. Holy cow. Did not expect this video to go on for as long as it has. Okay, so yeah. So we have that flag.parse, so we can actually get the value. I'm going to do res address. We're going to go ahead and resolve that via, resolve UDP address. Yep. Thanks, Copilot. And now I'm going to turn you off again because you sometimes get in the way. And this is about me typing and learning, not about you suggesting things for me. Print line failed to resolve resolver address UDP. Not sure. Tired. But yeah, if that happens, then you're trying to give us a resolver and it's not working, so we're just going to go ahead and return early. And then somewhere down here, what we really need to do is just use that resolver address, right? So we're handling messages, they're coming in. We have our response code checking that we're doing. Sure, right down here seems good. So we can do if res address is not nil and response code is not equal to, well, let's just say if it is equal to 0, since we know that's the good case. We can do something like var all answers, resource record for question in range, message.questions, something like that. Create a single query like so. It'll be a query. It's going to have a header. That header is going to be a header. ID is going to be message.header.id. QR is going to be false because we don't support that. Opcode, message.header.opcode. AA is false. TC, false. These are all values that we've set before. In fact, I probably should just copy and paste them, but I'm on a spree, so I'm just going to keep on going. Message.header.rd. RA is going to be false. Z is going to be 0. R code is going to be 0. QD count is going to be 1. AN count is going to be 0. NS count is going to be 0. AR count is also going to be 0. We need to give it questions. Questions are going to be question. And it's just going to be that question that gets passed in. Answers is going to be a pointer to a resource record. And we'll keep this empty for now. We can do something like query data is going to be single query dot encode. And then we need to essentially dial up that UDP connection. So we'll get a con here. Could be an error. So net.dial UDP. Yep, that one right there. We need to tell it that it is UDP. We can give it nil for the local address, and then for the remote address, we want our res address, like so. If error is not equal to nil, thumped printline that bad boy. Failed to dial resolver. Continue. Otherwise, we're going to get some bytes. I don't really care about the bytes, so we're just going to do con.write. We're going to write to that connection our query data. If we get an error, we'll handle it by con.close. Continue. I probably should do a print line in here somewhere just to let us know that this did happen. Unable to send query to resolver. No new variables on the left side. You got it. So something like that. And then we're almost done. We should just be able to take this and get response data. We know that there's a hard limit on the size of this. So let's go ahead and create our byte slice with 512. We can get n bytes, I guess, our byte length from con.read. And then we'll read that into our response data buffer. We'll call con.close now that we're done with it. If error is not equal to nil, thumped print line. Failed to read from connection. We can continue. Resolver response, response error, parse message, something like that. And then we need to pass in response data up until n bytes. So we're going to subslice that. If error is not equal to nil, man, I'm getting tired of typing that. Thank you, Go. Failed to parse message, something like that. And then we can also continue in that case. We don't want to necessarily break because we still want to keep trying to handle messages. In this case, maybe they sent a bad response back. It's not something that should crash our application or exit our application. It doesn't have to be like a panic or a crash, but you know, if we break out of our for loop that is holding our application open, it would end, and we don't really want to do that if they sent a bad message, right? We can just discard that, ignore it, and move on. So then we're going to append all answers, and then we want to append resolver response dot answers. We'll spread those. Thank you. Good job. And then we need to create a final response out of all of this, right? So now that we have all of our answers, we can come down here, say something like final response. This is going to be a query. It's going to be a header. We have a header again. ID is going to be message.header.id. QR is true. Opcode is going to be message.header.opcode. AA is false. TC is false. Again, these are values that are instructed by Codecrafters to set to either 0 or 1 for the sake of this challenge. So that's where the false and the true are coming from. So we have our header, we have our RD value that we want to get. Our RA is going to be true, whether we support recursion or not. Z is going to be 0. Our R code is going to be 0. Our QD count is going to be a uint 16. It's going to be the length of messages.questions. Sorry, not messages, message.questions. And then our AN count is going to be a uint 16, length of all answers. Our NS count is 0. Our AR count is 0. And then we need to add our questions, which is going to be message.questions. And then our answers are going to be all answers. Whew, okay. Let's get our response bytes from final response.encode. And now that we have those bytes, all we need to do to wrap this one up, I believe, is take our UDP connection, write to UDP, Response bytes. What else do we need? We need, the source, which is our address. If error is not equal to nil, we have something that went wrong. Print line failed to write response to source, something like that. And then finally continue. Okay, I feel pretty good about this one. Let's just give this a commit. Let's add git commit, add resolver. That's how long it's been that my GPG keys need to be refreshed. We'll give this a push and let it run. I think this should cover it. One thing I'll say while this is running is DNS is really interesting. It's from the work that I've done with this and just the research that I've done as well. It's actually pretty simple for how much it does. This is going to sound contradictory, but it's pretty simple for how complex it seems. Like, it seems like it's doing so much. It powers the internet. It's something that was built a long time ago and is still standing today. And it's pretty simple in the grand scheme of things, which I think is pretty neat. So what we did with this forwarding server, we marked the stage as complete. Again, what we're doing is if you pass in a resolver or a forwarding server, I don't even remember what the flag was. We can find out here. Flag might not have been the best search there, but resolver. So if you pass in a resolver, instead of us trying to figure it out, we're just going to ask someone else, and then we're going to get the responses back from them. And then we will bundle those back and send those back to the person that asked. So that's really what this last stage was doing. I'm going to mark the stage as complete so we can get our confetti and then hit go to next step and get the challenge complete piece. Only 15% of users that attempt this challenge end up completing all stages, and you're one of them. Yeah, that compressed packet one was a little rough. So here's what you can do next. Polish your code, publish to GitHub, try a different approach. I'm good. I don't need to do those things. If you follow along and copied my code verbatim, you probably should polish your code before you publish it anywhere. But for me, in the 2.5 hours that I've been recording this, this is good enough, and I'm happy that we've completed the challenge together. So hopefully you learned something about DNS. Hopefully maybe you learned something new about Go, or something that new patterns to adopt in Go, or new things to try. Maybe you've never worked with UDP before, so now you've seen how to work with UDP in Go. And if you haven't yet, consider subscribing to the channel. I would love it if you joined us for more adventures in coding, whether it's Zig or Go or whatever other fascination I have for the week. I would love if you were a part of that. And so much so that also, if you wanted to, I have a Discord server that you could join, and we have fun little conversations about all sorts of little things. And I would love it if you were there as well. So I'll put a link for that in the description below. I'll also put a link for Codecrafters in the description below. I think that one thing that is really cool, I've mentioned this previously, they do free stuff. So Kafka's free during the beta. I feel like they usually have one free every month, but maybe they've changed on that. But this might be a fun one. Also, it sounds like a very challenging one. But something to think about. Actually, this one has a lot to it too. So if you haven't yet and you're interested, sign up for Codecrafters with the link in the description. It's in full transparency, it is essentially an affiliate link. You don't pay anything to sign up with my link, but if you do decide to convert to a paying customer at some point in the future, I get a kickback, and that helps me keep the channel going, make videos like this, and really just make sure that I'm able to make the time to do longer form content like this, or longer challenges and things that hopefully are interesting to you. Also, you never have to convert. There's no pressure. And I'll stop talking about that now. Sorry, 2.5 hours straight of coding, and I'm a little tired. I think that's it. So thank you very much, and have a great day.